what's the problem that we looked at last time?
It's like the shortest paths with like the levels and the like decremental thing, right?
Right. So the setting is you have a graph and you only delete edges, right? And you want to maintain single source shortest path. And so in unweighted graph, what is the running time that we get? Mn, yeah. So unweighted Mn. What about, and like if the weight is W, W is like max weight, then the trivial way to solve this setting is just to increase the max level to something like NW, and that will give you this time. Right. But we show how to speed this up, and anyone recall what's the kind of running time that we get?
And then epsilon to the -2 log W.
Right. Something like Mn over epsilon for each scale, and that's going to be like something like this mini scale. But this is now like 1 plus epsilon approximate. Okay. That's the type of running time that we got. Okay. And the goals of today is to improve it further. We want to spend time that is like close to n square. Okay. So this is going to be kind of at least near optimal if the graph is dense. Okay. The total time to maintain the whole thing is just close to n square. Okay. Right. And like the key idea that we get to this algorithm is that we basically probe edges less often, right? We probe edges less often. Basically, we just probe edges after the level of the endpoint change by quite a lot. Instead of once the level changed by 1, we just probe it. We just now like say that we just force the level to change a lot, like in the big jump each time. So we just probe it after the level change a lot, and that basically speed things up. Okay, and now today we will, but the algorithm was just probing each edge. Each edge is still probed with the same frequency. And today, the key idea is that we don't need to probe every edge with the same frequency, and it will speed things up. Okay. So that brings us to this data structure. Okay. So we had shown before like that. If you have a graph, you can maintain tight edges of a graph under label increase. Okay. And now we're just gonna try to speed things up by just only maintain the approximately tight one. Okay. So maybe I recall the same set, like the setting is this, right? The setting of this data structure, the approx tight edge data structure is the same setting as the tight edge one. Okay. So in this setting, we have a graph G, and we have a label L. And what we want to maintain is the active edge set, which intuitively you should think of it as tight edges, or approximately tight in this case now. Like it used to be just the set of tight edges. Now it's going to be approximately tight edges. Okay. We maintain this set, active set, or in the literature is called admissible set E prime. Okay. And the update is the same. You could relabel, increase the level. Okay. When increase the level of U when there is no active edge incident to it. There is no active edge out of it. Okay. Or you can update an edge. Okay. Good. You can delete things, you can insert a relaxed edge. Okay. Do anyone recall what was the invariant of tight edge data structure from previous class? What was it? There are two invariant.
One was all edges are relaxed.
Yes, exactly. All edges are always relaxed. That's one. And another is about the active set. Yeah.
I think we mark an edge as like active only when it's one stretch.
Exactly. So we want the set of active set here to be exactly the one that is stretched. And since because everything is relaxed, if it's stretched, then it's tight. So it used to be that this set is exactly precisely the set that is of tight edges. Okay? But here we're gonna change it a bit. We're gonna relax it a bit. Okay? The first thing is that all edges now are just 1 plus epsilon relaxed. So it used to be 1 relaxed. Now we allow it to be a bit stretched, a bit overstretched by 1 plus epsilon. Okay. Next is that we want this set E prime to be basically approximately tight set. And now what do I mean? I mean that if it is quite stretched, quite overstretched now, like if it is 1 plus epsilon stretched, then it must be active. So if it's really stretched, then it's in our set for sure. And also, if it's in our set, active set, then at least we know that it's basically almost fully stretched. It's 1 minus epsilon stretched. Okay. So this set, the active set here, right? If an edge is really stretched, it's 1 plus epsilon stretched, if it's kind of overstretched by 1 plus epsilon now, it's in our set for sure. And if it's in a set, then we know that it's quite stretched. It's almost fully stretched. It's 1 minus epsilon stretched. Okay, so that's the invariant. Okay. And the point now is that we can maintain this approximately tight set with this graph G label L and this maximum label H and this approximation parameter epsilon in this time. In total update time of this one. So this used to be MH, right? It used to be basically sum over all edges and times H. Basically, we used to just pay H per edge. But now, we're gonna pay, like, for each edge, we're gonna pay H over epsilon times weight. So the higher the weight of some edge is, the less often we pay, the less we pay. Okay. That's the first term. The second term is just the number of nodes times H. And the third term is the number of edge update. U is the number of edge update. Okay. So this is just the important term. We improve from MH to this one. Yeah. Which is, we basically pay less for the weight, for each edge that it have high weight. Okay. All right. So now the algorithm is going to be almost the same. Okay. And just supernatural one, which is how do we maintain the approximately tight set E prime? What we're going to do is just for every edge, okay, we're going to probe them whenever we need to. But when should we probe them? We used to probe them whenever the label of U or V, the endpoint, whenever it changed, we just probe them. We used to do that. But now we do it less often. Whenever like the endpoint, the level of U increased by epsilon W, or the level of V increased by epsilon W, then you probe. Okay. So, and what does it mean to probe? Then it's just the same here. If it's one stretch, then we mark it. If it's not, then we unmark it. Okay. So again, just for some, let me draw something. It used to be that when, if this is U and V, right? And maybe it's like this. Okay. It used to be that whenever like this level changes by a bit, by one, we're just gonna probe them. When you increase the level, we just probe this edge all the time. But now we kind of just say that the granularity of how we probe should be more coarse-grained. So we just say that let's put this, and this is like a epsilon. And whenever like, yeah. So whenever like the label cross the red bar, then we probe an edge. Okay. So this granularity for each edge is different, right? Okay, is it clear? Okay. And how do you relabel and how you update an edge? That's just straightforward again. If you relabel, just increase the label. If you update an edge, just add or delete that edge. That takes constant time. Any question about the algorithm description? All right. So let's see that this invariant is maintained first before we analyze the running time. The invariant that everything remain almost relaxed, 1 plus epsilon relaxed. And another is just that if it's stretched, then it's active. If it's active, then it's 1 minus epsilon stretch. Okay. Let's prove it like one by one. So first, if E is 1 plus epsilon stretch, then I claim that it must be active. Okay. So imagine that, like, imagine the time, how can H become 1 plus epsilon stretch? At the point, the previous time, at some point, E must be 1 stretch first. Okay. And it will become more and more stretch because the endpoint keep increasing, the level keep increasing. And after E is 1 stretch, and at some point it become like, before E is like more than 1 plus epsilon stretch. Then the level of E here, like this, if this is E from U to E, yeah. When you keep increasing the level of U, after this is 1 stretch and before is more than 1 plus epsilon stretch, the level of U must have been increased by at least epsilon W. But if that's the case, then we must have probed the edge, and then we would have marked it, and it would be in E prime. Okay. And then I also claim now that like every edge will stay relaxed, 1 plus epsilon relaxed, not too overstretched. Why? Because once an edge is in E prime, then the endpoint U, the higher endpoint here, you cannot relabel U. You cannot increase the level of U just by our promise that we will not relabel U if U has some active edge out of it. Okay. So if you cannot increase the level, then it means that this edge E will not become more stretched after this. Okay. So it will stay 1 plus epsilon relaxed until it's actually until E is not even active. Right. So yeah. And when we kick E out of active set, it means that E is not even E is not 1 stretch, so it's less than 1 relaxed. So it's kind of quite relaxed now. Okay, good. So this invariant is true. This invariant is good. And next is that if an edge E is marked, then E must stay quite stretched. Okay. So why is that? So know that when E is marked, if U and V is marked, then at this point it is 1 stretch. Okay, it's at least 1 stretch when E is marked. But this edge can become a bit more relaxed actually, right? How? Because U cannot increase the level now if it's marked, but we can still increase the level. If we increase the level, then the edge become more relaxed. Okay. But I want to say that the edge cannot become too relaxed as long as it's marked. Why? Because when it's marked, it's 1 stretch, but when an edge is becoming too relaxed, before it's becoming too relaxed, less than 1 minus epsilon relaxed, then the level of V must have increased by quite a lot now. By how much? By epsilon W. But if that's the case, right, then we must have probed it and unmark it if it is actually not stretched. Okay. So are we good now that these 2 invariants are actually maintained? Okay. So now let's see why the running time is this. Okay. Okay. So anyone want to explain? Actually, this is quite straightforward. Why do we pay this much? Where does this term come from? Yeah, okay.
We only update every 1 over epsilon times the weight of the edge level increases. Mm-hmm. And there are at most 2H level increases between those 2 things. So that's how many possible for each edge.
Exactly. So basically you focus on one edge E, right? And you ask how many times we're gonna probe this edge? E. So it increase the level can start from 0 up to H, but we're gonna probe them only like with this granularity. Yeah. So the number of probe here, the number of probe is at most H over epsilon of the weight. Okay. So each edge we're just gonna like spend time to probe it this many times. So this is just the total time to probe an edge, to probe all edges. What about this one? Why do we spend this time?
We have to like check the levels of each vertex whenever we do an update.
Yeah, like this is just, it's really just a time to relabel. Like every node can be relabeled H time. That's the time to just spend on relabel. Yeah. That's the time to spend on relabeling. Yeah. And this is just a time to update an edge. Each time we spend time to update an edge, we just spend at most constant time. There are many updates, so that's why this is here. Okay. Right. By the way, note that, okay, we spend this time because each edge is probed at most this many times. And this is just because each vertex is relabeled at most H times. By the way, note again that if we have those kind of the same trick we did last time, where like we force the label to be always multiple of K, then this total time for relabeling would be improved, right? Instead of VH, it's going to be VH over K, because the number of relabeling is instead of H per node is H over K. Okay. So with this, we basically now we see that okay, under label increase, you basically can still maintain tight edges approximately within plus 1 minus epsilon, plus minus epsilon. Yeah. Okay, so now let's see how to use this. Okay. So the goal now is to get approximate shortest path, approximate decremental shortest path on DAGs in this time. So the setting is just the same. We have a DAG, it's weighted. Okay? And because it's a DAG, you have topological order. So what is this? Well, if it's a DAG, like this, then you can put every node into, you can put number to each node. Okay. So that we know that if this is topological order, so like if basically U can reach V, then the number of U, the order of U is at most the number of V. So, and this number is like just between 1 to n. Okay. Is it clear? Like, are we good with this concept, topological order? Okay. Just to assign the number 1 to n to every node, to each node. Okay. different numbers 1 to n, so that this is true. Okay. And we have a sink again. We have a parameter d and the threshold d and epsilon here. And the update is that you keep deleting edges, and we want to do the same thing, which is maintain approximate ball of radius d. That is, for every node that the distance to t is at most d is in the ball, and if it's in the ball, then the distance is basically close to d. But we're gonna do this faster. Okay. So here's the algorithm. We initialize every label to be 0 first, and now here's the important part. We used to just say that we set the weight of every edge to be the weight and round it up to multiple of epsilon d over n. Now I'm gonna kind of increase it a bit further. By how much? By this much. This is another multiple of 1 plus 1, another multiple of epsilon d over n. But how much here? It's basically the difference between the order of u and v in topological ordering. So for example, if this is a path, if the graph is a path first, okay, and maybe there is this one edge here. Okay. So the topological this number, the difference here is just 1, 1, 1, 1, 1, 1, 1. But for this guy, for the one that kind of skip the order by a lot, we will increase the weight of the blue edge by a lot. Okay. So that's the first important thing. And the next important thing is that, okay, E prime now is just basically the same thing, but instead of tight edges, we just maintain the approximately tight one. We use this weight W, but now we allow some slack of tightness by epsilon factor. Okay. And the set B is gonna be all nodes whose label is something close to D, okay, at most D. Okay. The label here is 1 plus 4 epsilon D. But at the end, we will show that if the label is at most this, then the distance is 1 plus 6 epsilon D. Okay. So there is some difference here. Okay. Right. So now after this, everything is the same. When we delete, just delete that edge. And we maintain the same thing. That is, okay, as long as there is some node whose level is not maximum, and there is no tight edge out of it, there's no active edge out of it, then just increase the level. By how much? By a multiple of, epsilon d over n. So we have the same, this is kind of the same thing that the label is always multiple of epsilon d over n, and all edges, all edge weights are multiple of epsilon d over n as well. Okay, so that's the algorithm. Okay. So it's almost the same except this part. So now let's see why this is good. Okay. So first, I claim that for every node whose level is not maximum, then the level here is basically the distance, but up to like it's the distance from V, the level of V is just the distance from V to T with respect to W prime, not W. Okay. Okay. So why is that? Well, because we know that, what do we know? We know that first, let's look at this thing, right? This is at most 1 plus epsilon distance. This is relaxed with respect to W prime. Okay. So because all edges are relaxed, they are relaxed with respect to W prime because we maintain like the approx type edge here is with respect to W prime. Okay. So all edges are 1 plus epsilon relaxed with respect to W prime. If all edges are relaxed, then the difference between the level of T and level of V can be overstretched by 1 plus epsilon. So this thing is at most 1 plus epsilon the distance. Okay. But what is level of T? 0. We never increase level of T. So we get that, we get this side. Okay. For another side here, what do we know? We know that V has a stretch path to T. V has like 1 minus epsilon stretch path to T. Because level of V is less than H. Do you see why like, first of all, do you see why V must have a stretch path to T? Why is that?
Because we maintain the or we make sure that the active set for each node is non-empty.
Exactly, right? For everyone whose level is less than H, as long as the active, like it has no active edge, we just increase the level. So if V has level less than H, let's say this is H. So everyone here is less than H. If V has level less than H, must have some active edge out of it, right? Everyone has active edge. Okay. And everyone except T has active edge going out. So if every node has one edge going out except T, then there must be a path from V to T. And everything here is active. Everything here is active, so the active thing here is like 1 minus epsilon stretch. So it's quite almost fully stretched. Okay. So V has this 1 minus epsilon stretch path to T. But if it's almost fully stretched, it means that this thing is at least 1 minus epsilon distance with respect to W prime. So we get this part. Okay. So now keep in mind that like this, we used to have that this thing is exactly distance with respect to W prime. Now it's basically approximately the distance with respect to W prime. Because all edges are kind of relaxed basically, and the one whose level is not maximum have almost stretched path. Okay. So now, okay, so let's prove that. Now let's from here, let's prove what we want about B, this thing, right? If the distance is small, it's in B. If it's in B, then the distance is basically small. Okay. So if the distance, if it's in B, okay, we want to prove that the distance is small, basically, like within this vector. Okay. So what do we know? If it's in B, by definition, we define the set B to be the one whose level is less than this much, which is less than h. This is less than h. Because h is like 2D. But if it's less than h, then the level here is at least this much. Because the level is less than h, it has a stretch path. So the level is almost as big as the distance. Okay. But once we have this, how can you conclude that the distance with respect to, so you know now that the distance with respect to W prime is basically small. Okay, you have this factor. So now, can you tell me why the distance with respect to W must be small too? Like why this should be true now, if the distance with respect to W prime is small?
I mean, I don't know why like those exact numbers, but like W, we still didn't change W by that much to create W prime. There's like just the dependence on the topological ordering and then some rounding.
So it's actually simpler than that. It doesn't really matter how much we change W prime. Anyone? How did we define W prime from W?
Well, we rounded up the original weight of the edge
We
to
just,
the nearest multiple, and then we added like epsilon d over n
Yeah.
times.
we do something, but we only increase, right? We only increase W to W prime. But if the distance is small in W prime, it must be small in W too, because we only increase.
But where does the 6 come from then?
The 6 just come from here. So we get that 1 minus epsilon times the distance W is at most this. So it means that distance with respect to W is at most this much over this one. So now I just make it like 6 instead. So it just comes from this thing. Okay, good. So this direction is kind of not like, it's not specific on how we change W to W prime. It's just with respect to that, we use just the fact that we increase. But how exactly we increase W now, we'll use it in this direction. If the weight is at most D, then it must be in B. Okay. If the distance is at most D, then this node is in B. Okay. So let's consider the path P, which is the shortest path to to T, from B to T with respect to W, with the real weight, original weight. Okay. And now let's see how much W prime increased the weight of this path P. We have that, you have the, look at the path P, look at the weight W prime. Well, it will increase the weight of W. But by how much? By this much. For every edge in P, we round it up by this multiple, by this factor. So we pay for every edge E, epsilon d over n. But not just that. For every edge in edge AB in the path, we also increase it by this much times epsilon d over n. Okay, so this is exactly how much we increase. Not exactly, but at most, like the upper bound on how much we increase. Okay. But now I claim that both of this is at most. I claim that this is at most epsilon d. This should be easy because there are at most n edges in the path. How about this? I claim that this is at most epsilon d too. Why is that?
Because of the topological order, the difference between like the numbers we assign to each vertex, if there's an edge between them, it's at most n.
So it's true that each of this is at most n for sure, because topological ordering is between 1 and n. But why the sum here is at most n, actually?
Kind of a similar argument to the maximum edges in the path, because we know that like maybe the shortest path is like just one edge or something, but and it's on the path graph or something, which is like the worst case. But if we're going from the start to the end, then like the total difference in topological order needs to be n.
Exactly. Consider this example, right, where it's like a path. Every path go forward in topological ordering. There can be n edges where like each of these different here is 1. There can be some path, some edge that like actually this is big, something like n over 2. But there cannot be too many edges like this, right? Like in total, we just always go forward in the order, and we just go forward in the order by at most n. No matter what, like you can go forward by here in tau by at most n. That's why this sum is at most n. Okay, so sometimes this can be big, but the sum is still at most n. Okay, so then you get that this one is just, this is at most d. So this is 1 plus 2 epsilon d. But okay. But now like we know that all edges are epsilon stretch. So the level of V is at most 1 plus epsilon times the distance with respect to W. The distance with respect to W is at most this one, because this is just some path. This is the path, shortest path in W. It's not shortest in W prime, but it's just some path, which is like more, at least the distance in W prime. But this thing is at most 1 plus 2 epsilon d. So in total here is at most 1 plus 4 epsilon d. So we get that V is in B. Okay. So we now get that like within, oh, okay, good. So we get the correctness. What about the time? Okay. Let's analyze the running time. I claim that it's going to be something like n squared now instead of mn. So because our label is like a multiple of epsilon d over n. So now we get that the approximate edge data structure will have this running time. Maybe before I go. Okay. We have this term just because this is how much we probe each edge. The number of times we probe each edge. But because the level is the multiple of this thing, so the total time for releveling is reduced by this factor. And we have U here is at most M, because we only delete. Okay. But now we can analyze, right? Okay. The weight here is upper bound, is a lower bound by this much. Because for every edge, we increase it by this much. And so, like, this thing might simplify to n squared over epsilon. How about this? Like d here cancel, and you have epsilon square here, and you have n here, so you get n over epsilon square here, and then you get this term. Okay. Right. And how big can this be? So, for example, I claim that this thing is at most n log n. So why is that? Let's look at this term. Okay. When I even let's say I fix one node u, okay. And even if I have edges from u to everyone, and everyone to you, like in this order. Okay. When I sum this thing, it looks like I sum over 1, 1 over 2, 1 over 3, 1 over 4, and so on. This is 1, 1 over 2, 1 over 3, 1 over 4, and so on. So this is at most this sum, like 2 over I, starting from I up to n. But this is a harmonic sum, which is log n. Okay. So like this term, when you sum over all edges, I just focus on one node and sum over all edges incident to you. This term, for the one incident to you, you just pay log n. And there are n nodes. So we pay in total here n log n. Okay. So we are done. Question? Okay. All right. So you see that the key to improvement here is that when an edge have large, are far away in topological ordering, we probe them less. Okay. So the frequency of how much we probe each edge is different. And why does it work intuitively? Again, when we are on a DAG, right? Every path contains only few edges with large different in topological ordering. So because the sum of this thing is at most n. Yeah. And so what do we know? We know that the guys that are kind of far away in topological ordering, there are few of them. So if we know this, if there are few of them, then the edge that have this large different in topological ordering, there are few of them, so it's okay to make error on them quite a lot. In the previous algorithm, we just said that for every edge, we round it up to some multiple of epsilon d over n. So we just kind of pay additive error the same way, uniformly for every edge. But now we kind of know that for the guy that have this thing large, there are few of them anyway. So it's okay to just pay large additive error on them. Okay? So that's why I say that, okay, for this edge, I just add this additive error to them. Okay. Because the guy that gonna pay large error here, they're not too many of them. Like if we set it like this, the total additive error is still gonna be small, as we have seen. Here. This thing is small. Okay. But once we know that we can like pay large additive error, which is basically to increase the weight. When you increase the weight, that's good for us, right? Because the larger the weight increase, the less often we can probe them. So that's the idea. We just try our best to like increase the weight, as long as it doesn't make too much error. Once we do that, the approx tight edge data structure will be faster. And by how fast, like we know that every edge has this, it's at least this much. And now we use this fact that like this sum is at most log n. And from here we can conclude in log n square time. Okay, are we good? Okay, so we're gonna basically use this idea, so this is kind of the part about dynamic choice part that I want to tell you, how to get mn and how to improve it to n square on DAGs. And then we're gonna do the same thing for MaxFlow. There's gonna be mn algorithm for MaxFlow and n square algorithm on DAGs. You're gonna see how it just go in parallel, the same thing happen. But the cool thing is that by the end of the course, we're actually gonna get n square, not just on DAG, but on any graph. How to do that? We're gonna use exponent hierarchy. Yeah. Good.